So I'm going to be talking about FPGAs, and I'm going to use Nekbone as a bit of a vehicle here, but I actually want to talk a little bit more general about the architecture. And I appreciate there's lots of people who might not necessarily know what these things are, what reconfigurable computing is. So I want to start by just giving you an illustration where what we have on the left is really a view of how computation progresses traditionally. And this is probably how a lot of us learn to program, where we've got this idea of a flowchart, we've got our code, and we see it executing one thing after another. And here we have a loop, and it goes round, and it executes one after another, and it goes round, etc. So this should be very familiar to a lot of people in the audience. However, there is another way, and the other way is with what we call spatial computing, Dataflow computing, etc. And that is this thing on the right. And that's where all the logic that makes up this program, here are all our steps, are laid out onto the chip so that they can run concurrently, a bit like a big pipeline on the right. And what we do is we shovel data in. So we shovel the first element in, which then comes into here, and as it's processing this is then working on the next element. And then this first element goes down here, the second element down to here, and then the next element here. And as I say, like a pipeline, once this is fully filled, then the idea is every clock cycle, we're producing a result. Because we have this massive amount of concurrency with our program, as I say, laid out on the chip and all the different parts running concurrently. Well, that's the idea at least. Now, when I talk about reconfigurable computing, what that often means, certainly in our domain, is field programmable gate arrays, FPGAs. And if you're not so familiar with these, this is very special hardware because it is directly configurable at the lowest level to look like your application. So all these red things here are configurable logic blocks with lookup tables in that can be configured, as I say, to look like your application. And throughout it, we've then got a whole load of very, very fast memory, which are these, and then specialized circuits for doing things like arithmetic. And furthermore, some really, really fast connections to the outside world. So what that can mean for us is PCI Express, high bandwidth memory, normal DRAM, maybe sensors, Ethernet, etc., etc. So what we can do is we can configure this, as I say, to be a bespoke hardware accelerator for our application. We are getting rid of all these assumptions that the CPU or GPU designer made for general purpose applications. It's utterly specialized for what we need, but because it's reconfigurable, once we're finished, we just reconfigure it to look like a different application. So, I think these things are quite cool and quite fun to play with. But within the field of HPC, that's not enough. There's got to be a reason why we would ever use these things, why they would ever be part of a future supercomputer. And, I think there's three main reasons for this. The first reason is because often FPGAs, I think, can help us get around the memory-bound nature of codes. So this is where a code just can't shovel data in fast enough to the compute. And there's quite a lot of codes out there in HPC that are limited to some extent in this way. And FPGAs can really help there. Now, there's two ways that they can help there. Firstly, this massive amount of bandwidth to the outside world and within the chip. This is typically an order of magnitude greater than CPUs and GPUs, but also the concurrency. And for instance, what we can do here is we can have part of the chip working, doing compute, and we can have another part of the chip working, feeding in data for the next bit of compute, maybe reorganizing it, doing any sort of manipulation, so that when that compute needs it, boom, it's good to go. So we have a lot of flexibility how we deal with that, and we'll see this a little bit later in the talk. Another big benefit I think of is the ability to accurately determine sort of realistic theoretical performance that you can get from the code. You know what CPUs and GPUs are like. With a black box microarchitecture, you really never know exactly how it's going to run. But absolutely on the FPGA, because we're right down at that lowest level, we've got that knowledge. And also mixed and reduced precision. I'll talk about that again later on. Now, if you've used FPGAs in the past, you might have a slightly old-fashioned view of these things, and there's been a huge amount of development in the past few years to massively increase the ability to program these things, and I think make them much more accessible to us as software developers. And to give you a flavor of this very briefly, the first thing that's been done is what's called high-level synthesis. So this is where you can write code in C or C++, and this gets synthesized down to the hardware description level. It's a bit like compiling code on the CPU or GPU, and it generates the machine code. Whereas traditionally for FPGAs, you had to work at that hardware description level, you had to work at that machine code level, and it was way more difficult. So that sort of summation example I showed you briefly before, this is what it looks like in HLS for a Xilinx chip. Very sort of common C++ code, and we've got some specialized pragmas here that tell it how to handle it. And we use these pragmas to then direct the tool. But utterly understandable, OpenCL on the host to then drive this. And there are some issues here, and we'll talk about performance a bit later on, but absolutely this will build and this will run and it will give you the correct answer out. If you've at all seen or used FPGAs in the past, you might have seen something really nasty, such as this diagram here. And this is called the block design. And again, in the past, what we had to do is manually connect all the different components together. Things like the external memory with memory controllers, our own kernels over here, and then connections to the outside world. And again, we don't need to do any of that anymore. The tooling is mature enough so that it will generate all of this for us. And actually, this is a completely different view, I think, of the technology than even what we had a couple of years ago. Because now, absolutely, it is possible to be in that software world, to be working, really thinking about your algorithm from a Dataflow perspective, considering, how the design is going to be taking advantage of the chip, as we'll see, and not getting bogged down by these lower level details. And actually, I think that's a big thing that we in our community can provide to FPGAs, that sort of algorithm design as we're looking at porting some of our things across. So, as I say, I want to motivate this with Nekbone. And I don't know if you're familiar with it, Nekbone is a very, very popular proxy app. It represents the core computational kernel of NEC 5000, which is very popular. It was a Gordon Bell winning code quite some time ago. But when I took Nekbone and I profiled it, I found that there was a big challenge here. On the left is just the profiling from Intel VTune on one single core. It's given me about 5 gigaflops, slightly more, but you can see only half my cycles, slightly less, are green. So I'm throwing away more than half of the CPU power on it stalling for memory and other things. And actually the view gets even more bad, even worse as we scale up to run on all the CPU cores. We're going on to 24 cores of Cascade Lake, but it's only giving us a 12 times increase in performance. So parallel efficiency of about 50%. And you can see here now per core, the actual number of cycles that are useful is just over 25%. So, about 75% there or thereabouts is wasted cycles. So obviously a key question is whether the FPGA can help us here, whether it can help us get around the memory-bound nature of the code at all. And we're focusing on this AX kernel, which is the vast majority of the runtime for Nekbone. It's the solver part. And just to give you a sketch, it looks a bit like this. Actually, in the Nekbone code, it's Fortran 77, but all the tooling requires C or C++. So the first stage is to convert it into that language. And I thought I'd just keep with showing you one language, or else it gets a little bit confusing in the presentation. But what you can broadly see is we've got a whole bunch of elements, 800 in our configuration, looping over these, and for each we call this procedure, and then doing a whole load of sub-activities. So for instance, this thing here, we've got a matrix multiplication, lots of smaller ones, another matrix multiplication. We've got some multiply and accumulate here, and then lastly this thing here, which is again these matrix multiplications and some additions as well. And per element, and I say we've got 800 elements. Per element, we've got 4,000 grid points and about 800,000 double precision floating point operations per element. And it's all double precision at this stage. Looking at seeing if we can accelerate it on that piece of hardware on the right. So I talked about these configurable bits of the FPGA. It's got over 1 million of these. It's got over 10,000 of these specialized circuits for doing arithmetic. It's got 41 megabytes of this really, really fast 30 terabits per second on-chip memory, and also some high bandwidth memory as well, and then some slower memory on the board that we're not too concerned about. And this is a state-of-the-art, absolutely state-of-the-art accelerator as it stands from Xilinx. So we take the code, we do this decoration with the pragmas, and then, very acceptable, I think, to a software developer, we just use this V++ command over here. Looks a bit like doing the compiler on the CPU, and it builds it for us. Happy days. But the big problem is, whilst it will build it for us and it will run correctly, the performance sucks. This is the performance on our 24 cores of the original Fortran code, and this is the initial FPGA performance. When I calculated it was 0.03% of the of what the CPU is giving us. So even though it converts it correctly for us, clearly there's a lot of work that we need to do, and we'll talk about in terms of improving the performance and really specializing it for the chip and for this data flow view. I'll talk about the theoretical performance on the next slide because it's slightly easier to explain on that one. But the tooling itself gives you a whole bunch of feedback, which you have to learn, you have to know what it means. But if you've got experience with it, then there's certain things such as that and such as that, which are red flags, and say, look, you need to start thinking about improving the algorithm at these different points. So based upon that feedback, what we did is turned it into something that's much more data flow, and that's this diagram here. So it all goes back to what I said at the start in terms of laying this out on the chip. So we've got all these different things running concurrently. So each of these matrix multiplications you can imagine is a different part of the FPGA running concurrently, getting data streamed in, processing it, streaming data out to another part of the chip, which is processing it, and then streaming that out, etc. So these are all running, as I say, at the same time. And then within each of these matrix multiplications, we initially adopted this algorithm here, and it's actually based on one that Xilinx developed in their open source library. So we built that, we then did some performance runs, and it was slightly better. It was actually 20 times faster than our initial code, but it was still way slower than the CPU. Now we were at 0.6% of the CPU performance. So still, clearly there was more work to be done. But what we can also do at this stage is, based upon this current design, work out what I call our theoretical performance. And that is the fact that each clock cycle, purely from looking at the code, what I can say is each of these matrix multiplications is capable of doing one floating point operation. So we've got 6 of them, that's 6 floating point operations. And this middle thing in yellow, this local accumulation and multiplication, that's doing 17 floating point operations per cycle. So we add them together, we multiply it by 300 million because we're running at 300 megahertz. And what that tells me is my theoretical performance as it currently stands is 6.9 gigaflops. Now, you can see at the bottom, we're nowhere near that, but it's really saying, from the perspective of the way I've designed the algorithm, if I could get the data streaming through and every single cycle productive and keep things flowing that data through, then actually that's the performance I should be expecting to aim for. And the fact that I'm so far off it, 6% of that, really illustrates that there is a big bottleneck here which needs to be optimized. So in terms of looking at this, where that bottleneck lies is actually in this matrix multiplication algorithm. And the big problem here is the way it was designed. And if you look at this, remember what I was just saying in terms of wanting every cycle to be getting data streamed in, data streamed out, and making progress. But we only stream out data here with this write on the last iteration of this outer loop K. So NX here is 16. So for the first 15 iterations, we're doing all this work and not producing any results. And then lastly, we start to produce them. So that's a major problem, a major bottleneck. So not only did we refactor that, really with this view of keeping the data fed, keeping all these things running at the same time, but also we took the opportunity to refactor the algorithm as well and effectively do some loop unrolling. Moving from being able to do one floating point operation per cycle for each of these matrix multiplications to when we unrolled it to do 31 per cycle. So what that then meant is we had 31 times 6 of these, plus 17, 61 gigaflops was our theoretical performance that this increased it to. And by doing that change, and also by, once all this has been filled from the pipeline perspective, starting to produce the results, we had a big increase in performance to 12 gigaflops. So now we're 20% of the CPU, so we're closing it down, we're not there yet, and we are about 20% of our theoretical performance. Again, certainly room to optimize this, but we're improving. I say thinking about the hardware and matching our algorithm to that hardware. So at this point, I realized, well, there's something that I really am missing because I'm still falling short quite considerably. And what is it? And what I realized, it was in fact the way in which we designed the data flow because of the limitations of the way in which the algorithm works. The big challenge is this U that we've got up here. It's read in for each of these matrix multiplications, but for each element, it's consumed in a different order, in that one, and that one, and that one, than what it is in memory. And it's the same for down here. Each of these is producing intermediate values, but the order in which they're produced, these 4,000 grid points, is different from the order in which they're consumed. So we have this data buffering. I was reading the data in, reading these 4,000 grid points for an element, and only once they've been read in, then start feeding them in here. And then this would work. And again, I would store those intermediate results, and only when all those intermediate results were available, I'd then feed them into there. So effectively, my code was running in 3 phases. This phase here, then this phase here, and then this phase here. And it was killing my concurrency. I was just not taking advantage of the hardware because there was lots that was sitting there idle because of this data buffering issue. So then the way in which we got around this is by using what I would term double buffering, but I think it's more of a hardware term to call it ping pong buffering, but they're the same thing, where instead of filling a buffer and then serving it out, instead we are concurrently filling a buffer for the next bit of data and serving out for the current bit of data. So what you can see over here is, imagine this middle bit, we're working on the current element data. Well, the previous part, we're now feeding in data for the next element and doing the reordering. And this last part, we're actually working on the preceding element, where all those intermediate results are available and we're processing that. And really it goes back to what I was saying towards the start, is if your code is fairly memory bound, because we've got this massive amount of concurrency, we can get fairly smart in terms of how we're using this to keep it busy and to keep that computation fed. And this had a massive impact on the performance. We did also do some slight refactoring as well that I've just omitted, but this was the main improvement here that got me up to 59 gigaflops. So now about 90% of the 24 core CPU, and I'm hitting about 97% of my sort of theoretical performance from doing that calculation. So at this stage, I know that there's not a huge amount of headroom to further optimize at the algorithm level, because I've got most of that sort of speed up that's possible based upon the design of this. And that really takes me to my last point about this as an example, because by using this theoretical measure of performance, my CPU was achieving 65 gigaflops, but the theoretical performance said, look, as you've currently got it, your FPGA can never do more than 61 gigaflops. So as hard as you push it, you're never going to hit the CPU. And there's 2 ways to address that. Firstly, to increase the concurrency of these floating point operations, but the other way is to increase the clock frequency. And that's what we did sort of at this kernel focus. We increased it to 400 megahertz. It sounds quite slow as far as a CPU or GPU is concerned, but this is pretty blazing hot from the perspective of an FPGA. And this really increased that theoretical performance, and suddenly now we were beating the CPU, the multi-core CPU, by about 18%. And it's certainly possible to push this higher, push this closer to about 500 megahertz, which is the limit, but you get, a law of diminishing returns, and you suddenly need to make the code way more complicated to enable that much higher clock frequency. Using a whole load of tricks, it's just not worth it. This is the sweet spot we found for this kernel. Now, what I'm going to talk about in a moment is scaling the number of kernels up, because we're only using here sort of a fraction of the chip. So we can obviously scale the number of kernels up to get us more performance. But just before I do that, just while we're focusing on this single kernel, I want to make the point, or the summary point on this, that I think it's really useful when we're thinking about data flow for this idea of a sort of an application-specific data flow machine. So, we're looking at all our different bits of our logic, I say spread out on the chip. The name of the game is to keep these continually consuming data, generating results each cycle. But then also, as I say, this really lends itself to this theoretical performance measure. And if your theoretical performance isn't sufficient, well, then you can go back, as I say, and increase that concurrency or increase that clock frequency. And I think that's really powerful. This concurrency gives us a lot, but also this theoretical performance measure gives us a lot. Now, what we then did is, I'd say, we scaled up the number of FPGA kernels, and we could fit 4 on the Xilinx chip. We also ran this on the Stratix 10 Intel's chip, and we could fit 5 on there. And we compared the performance against the CPU and also a V100 GPU. And what you can see is we are beating the CPU absolutely hands down. It's just simply no contest here. We're about 70% performance of the GPU, so we've still got a little bit of a way to close here. But interestingly, we are way ahead in terms of power usage and also power efficiency. I mean, the Xilinx FPGA is about twice as power efficient as the GPU, and about over 10 times what the multi-core CPU can provide. And maybe a slightly naughty comment, but if power is your only concern, is your primary thing, then actually we could, for both these technologies, have 2 FPGAs, still be under the power of the V100 GPU, and we'd beat it in terms of the performance. But obviously, you've got to be a little bit careful with those sort of arguments. But I think very interesting here, certainly for the U280, if we add an extra FPGA kernel, typically that's going to give us about 74 gigaflops performance uplift, and it's going to cost us about 7 watts. So, I think that's fairly interesting from these things. Really, sort of the last thing to say on this is a look towards the future, because this is current generation technologies, and if only we could fit another kernel on here, or do something maybe a little bit different. And that's where the next generation comes in, because what we've got coming is this thing here called the Versal, and this is going to be released later this year. Not only will there be some really significant advances to the FPGA fabric itself, this thing in the middle, but also what I'm really excited about are these AI engines, and that's this big thing over here on the right. And each of these are going to have about 400 of these AI engines. They're going to be optimized to heavily vectorize floating point or fixed point arithmetic, and potentially will be a game changer here, playing with the different levels of precision, and also moving to fixed point as well. On current generation chips, I don't see often a huge benefit moving to single or half precision. A little bit more of a benefit moving to fixed point, but I think this could potentially be a game changer, and will be really interesting to look at how to bring these things in and potentially close the performance gap against the GPUs, and maybe even beat it. We'll have to see. I say it's going to be quite an exciting year, I think, playing with all of these and just seeing what they can give with us on our codes. So just in summary, I think reconfigurable architectures are pretty exciting for the future. There's a whole bunch of different areas that potentially that they can give us, but it really obviously depends on the code. and really requires activities in order to explore this, how to write those codes, how to specialize them for the technology, and where the benefits are, and also where the low-hanging fruit is. I think currently a lot of the performance is fairly hard won, but as we mature this, often from our perspective as software engineers, thinking about the algorithms, thinking about the abstractions, then this will obviously get easier. And to some extent, it's us in the co-design space that are responsible for that. And certainly in Accelerate, we're looking at other codes as well from other partners, really to see the benefits in this can bring, but preferring where the codes are bound by memory or other aspects rather than computation, because that's where we see we can potentially do something quite special.